welcome everyone to the analysis seminar. It's a great pleasure to introduce Krzysztof Bogdan from Wroclaw, who will speak about optimal Hardy inequalities, identities and inequalities for fractional Laplacian on LP. Krzysztof.
Thank you. Thank you very much for the invitation, for the occasion to give a talk. It's my first time in Quebec, so let me start. This will be about some joint work and actually a program, research program that we carry out with colleagues from Warsaw and Wrocław, and occasionally from other places. I will focus on the first paper that you can see here, optimal Hardy inequality for the fractional Laplacian on LP, because it somehow shows that maybe it's a good direction, but I plan to also mention a few others. So the plan for today is to give definitions, which seem to be important here, to discuss the results. There will be 4 theorems that I plan to show, and then I want to give some insights about their proofs and actually the ideas that, in a sense, shape the proofs. And then maybe I will have time for remarks. Can you hear me well?
Yes.
Yes, good.
Thank you. And I have also a bit excessive bibliography at the end of the file, which I will probably not be able to discuss. But let's start. So here's about the beginnings of the topic. And the historical account is in a book of Kufner, Maligrand, and Persson. And the whole thing started over 100 years ago now. And Hardy proved this inequality that we see here for half-line, for functions which vanish at 0. And then, of course, there was a lot of developments. And in particular, the classical Hardy inequality in RD is this inequality with the gradient squared. And here we have a similar quadratic form. In a sense, this case of Hardy inequality, the initial Hardy inequality is a special case. Everything is the same. And of course, for d equal to 2, there's no comparison really, because there's 0 on the right. So such inequalities have many ramifications. One of them that is appealing, quite appealing to me, is that of Fitzsimmons, who proposed this formulation in the setting of symmetric Dirichlet forms. If we have a Dirichlet form E and a generator L, and if we have superharmonic functions, I don't really want to discuss this in detail what that means, but generally H should be non-negative and the generator of H should be non-positive, then we have such comparison for the Dirichlet form with the integral of u squared against the weight, which is negative LH, which is non-negative now, right, over H. So this weight, which sometimes is called Hardy weight or Rees charge, maybe, that gives the lower bound in the Hardy inequality. That's one setting that is easy to somehow refer to when we look for generalizations or ramifications. So I want to talk about fractional Laplacian, because in this case we will have some sharp constants, so that's maybe enough convincing. But the general setting could be more general. So let's talk about fractional Laplacian on RD. Alpha is between 0 and 2. That's my notation. This is a more proper notation. So this is a negative definite operator in a sense. Here we integrate the increments of a function u against the Levy measure density that has an exponent negative d minus alpha. So this satisfies the usual Levy condition. that is, it's not integrable, but integrable against z squared minimum 1. The constant is so chosen that the Fourier symbol of this operator is negative xi to the power alpha. So let us say here this requires, of course, the discussion of generator requires discussion of domain, but let me just skip this discussion and let's go to the Dirichlet form, quadratic form. Here's the diagonal actually part of this form. So in this case, the form is given by 1/2 of this double integral when we integrate squared increments. This is all very well known. The domain of the form are those functions in L2 which make this expression finite. So that's the L2 setting in a sense. Here's the Hardy inequality, classical Hardy inequality, actually identity for the fractional Laplacian. So let me discuss this because it must not be familiar to everybody. I should have alpha less than d minimum 2 rather than d, sorry for that. And the exponent beta is some parameter that we may want to maximize in a sense. Now it's just between 0 and d minus alpha. Remember that alpha is less than d and also less than 2. And if L is arbitrary L2 function, square integrable function, then we have the quadratic form from the previous page decomposes into a sum of two non-negative parts. The first one is this Hardy type expression, the right-hand side of Hardy inequality. And the second term is a certain expression which is probably best described in some kind of conditional or conditioned quadratic form. The same Levy measure here, this weight h, I will mention in a moment what h is. And here is the, we divide u by this h. In the same sense, conditioning is dividing or multiplying depending on context. This is identity. This is true for every function in L2. Here, h beta is x to the power negative beta with some constant. This constant kappa beta here is given by a ratio of 4 gamma functions. I should mention that Frank, Lipp, and Zeiringer have this result. This result is cited from Kim, myself, and Dyda, 2016, I believe. And but Frank, Lipp, and Zeiringer have the same identity, only on a smaller class of functions, like test functions with support outside of 0. Okay, I should say a few words about this kappa beta. So kappa beta is a function of beta. It's not maybe obvious to see how it looks like. It is symmetric. That's some simple, the structure of the function makes it symmetric with respect to the middle of the interval 0, d minus alpha. And here's the graph of the function as a function of beta on this interval 0, d minus alpha. It has a maximum, this function, it's symmetric as we said. The maximum is precisely at the middle of the interval, and it's equal, well, kappa d minus alpha over 2, which is this expression. So this is known to be the best constant in the Hardy inequality, because now from the Hardy identity we get the Hardy-Rayleigh inequality. It was differently called by people, and this is due to Herbst, Techner, and Yafayev. Different approaches to that inequality. So first of all, Hardy inequality is what people are interested in, but they may be consequences of Hardy identities, as we had on the previous page. So that's again L2 setting. The LP setting is what I want to discuss today. We will take P between 1 and infinity, sharp, and for any function u on Rd, I mean real function, we define this P form. We'll call it sometimes Sobolev-Bregman form or P form, and this is integral of expression which is non-negative. Let me explain what this power means. This is sometimes called French power, and this is a power which respects the sign. So a to k is the absolute value of a to power k times the sign of a. And this is an increasing function. Let's talk about k greater than 0. That's increasing function. So we have to increment the product of the increment of argument and the value increment of values of this function. So this product is non-negative. So this integral is well defined, and moreover, it satisfies inequalities. A comparison with the square of b to the power p over 2 minus a to the power p minus 2. So increment of this power function. That's again French power. The constant in this comparison are nearly optimal. That is, the left-hand side has the optimal constant, and on the right you could have, there is a constant, really the best constant, depending on p is between 1 and 2. And this is also well known. So the authors use it, and there is one temptation to reduce everything quickly, to reduce the study of the form EP to study of the form that involves just the increments of the p over 2 or the p half power. So I'm citing here some papers that give such inequalities. In particular, if you take the left-hand side comparison, we get a lower bound for EP. In terms of E2, applied to the function u to the power p over 2, and after simplifications, we get this inequality, and with the constant, here's the best constant for p equal to 2, and here's this extra factor coming from this pointwise inequality. And this is true for every LP function on RD. We are talking about RD here. For instance, this inequality is given in a book of Cialdea and Mazia and in other places. So our goal is to improve the constant. So again, recall this French power that was defined or discussed on the previous page. So for instance, the square root of the cubic root of x is x to the power 1/3, so that's the usual notation, but one should be careful with this notation. Perhaps we should teach our students to this notation, and of course some other authors don't pay much attention, they just raise x to power 2 and they consider this sign preservation as given. So, but we are using this notation, and here is the relationship in terms of the derivative. The derivative of the absolute value of x to the power k is expressed in terms of this French power. So that's somewhat important, because we now consider the second order Taylor remainder of this function x to the power absolute value of x to the power p. And if we consider 2 points, 2 arguments a and b, and look at the increments between a and b of this function, x to the power p, then we get this expression. So that's indeed the second order Taylor remainder of this function x to the power p. So for instance, f2 is the squared increment, f4 is given by this formula. In a sense, it has homogeneity 4, but there's this extra term. It's like b squared plus a squared, really. Okay, so this is an instance of Bregman divergence, which is a popular topic of in statistics, machine learning, and some such considerations, and probability as well. And I think it's useful to consider this on LP spaces. So here's some estimates of this FP. We already mentioned one estimate, here this one, and many authors use this estimate. And I want to also mention another elementary estimate All of this is very elementary, but maybe we should talk about this for a while. So the other estimate, which looks very different, but of course is equivalent in a sense, of course, because if we have an exact approximation, the two approximations, they must be approximations to each other. So let me explain what this approximation sign means. It means that the ratio of two sides of such a comparison is bounded below and above by two positive constants. So here is the one estimate that we are using in a paper with Dyda and Lux. And here we have just squared increment of the argument, and here we have the sum of absolute values of arguments to the power p minus 2. This is a little bit troubling for p less than 2, which is allowed, but actually the sign plus makes this kind of safe. Here I have some comments about comparison with the usual powers. Maybe let's consider this comment. This inequality, of course, means that left-hand side is less than constant times the right-hand side, and we don't care about this constant. And this is true for p less than 2. So why this is the case? If we take the right-hand side here and take p less than 2, then the exponent is negative. And so if we replace the sum of absolute values by the difference, then we increase this expression. And then we also get the right-hand side. So I'm explaining here very simple things just to get used to this notation. In general, this function fp, this Bregman divergence, is not symmetric in its arguments. We can consider symmetrization. And this symmetrization, as you could see, maybe let's look at this expression here and consider changing the roles of A and B. Then as you add two such terms, those p powers cancel, and then we get this product of increments. And this is exactly the kernel that we have defined, defining this EP. And again, I repeat what was already said, that we can compare, we can approximate this P form by the 2 form applied to the function u to the power p over 2. That's the consequence of this comparison. The last two lines are, I will have some warnings about that later on. So here is the first result that I would like to discuss. This is Hardy identity on LP. So I will use this notation h beta again to denote function x to the power negative beta. We are on RD. As usual, alpha is less than d minimum 2. That's somehow related to transients. And we have some interval for beta to have the following identity. So h will be h beta to shorten the presentation. The p form on u, arbitrary u in LP, is expressed as the sum of two terms. The first one is the, well, natural expression if we are looking for LP Hardy inequalities. There's some constant that we will discuss also more in a moment. And the second part is some kind of P form, but conditioned in the sense that we divide a function by the function u by h, and there are also some weights that appear here next to this usual Levy measure. The constants here are interesting, especially that for beta equal to d minus alpha over p, those two terms in the numerator simplify, and actually the ratio becomes this number kappa d minus alpha over p. Somehow we are using here the symmetry of kappa as a function of its argument. And if this is the case, that's the constant kappa d minus alpha over p. This is multiplied by this integral, and we can ignore the rest to get inequality from this identity. Such choice of this beta is optimal, which this is what we will explain or discuss in a moment, and that will be our optimal Hardy inequality on LP. Okay. Let's say a few words about optimality. So that's repetition of this Hardy inequality from the previous page. And I already stated this inequality from Mazier and Cialdea, which had the right-hand side with this constant. That's the best constant for the case of p equal to 2, and that's this extra factor resulting from the comparison of this Bregman divergence, basically. So first of all, our constant is bigger, at least for p different than 2, because for p equal to 2 they are equal. But here's a stronger result. This constant, this kappa d minus alpha over p, is sharp in this inequality 1. That is, we cannot have a bigger constant and still the inequality should not, I mean, to have this inequality true for every u in LP. So that's the second theorem. Before we go to the next result, here's a graph of the two constants for the dimension equal to 3 and for alpha equal to 1. This corresponds to the so-called Poisson semigroup or the Cauchy process and half Laplacian. This red line is our constant, our optimal constant, as a function of p. Here p is the argument from 1 to infinity, and the blue one is the constant that results from using the optimal L2 inequality and this comparison, this lower bound for the Bregman divergence. So they are quite close, but of course the red one is bigger. Okay, here are some other applications, some other results, and they are maybe not surprisingly related to Feynman-Kac semigroup generated by the fractional Laplacian. Remember, this is a negative operator, plus kappa times x to the power negative alpha. That's a potential. Kappa is a constant that has some possible range, and then x, that's the norm of x. So that's operator of multiplication. So the study of such operators is quite important. Part of the interest of it comes from the famous result of Taras and Goldstein about explosion, non-explosion result for such operators or semigroups on for the Laplacian, for the classical Laplacian, that is for alpha equal to 2. So let's talk about this p tilde, the Feynman-Kac semigroup corresponding to this operator. We have alpha less than dimension for transients. And then this operator is a contraction on LP if and only if kappa is less than this critical kappa, the best constant in the Hardy inequality. So in a sense, that's this if and only if shows that somehow we are on a good track to get optimal results for natural interesting semigroups. And here's a comment about the case of alpha equal to 2. Then we have the Laplacian plus this potential, and this is well known that it's known that the semigroup on LP is a contraction if and only if kappa is less than this number, which tends to be kappa d minus 2 over p as well. In this case of alpha equal to 2, our formula for kappa is also valid, but it simplifies. So there are two references to this result, actually three. So that's our third theorem, and I also will show this, we'll discuss this fourth theorem. So that's to complete the picture in a sense, we should say about the boundedness of this operator P tilde. So this operator is bounded on LP if and only if kappa is less than kappa d over P star, when P star is the bigger of P and the conjugate exponent. So this is less restrictive range of kappa. In a sense, we have fixed P here and ask about how large this kappa might be to still have a bounded semigroup on LP, and that's the range. I should probably say that if P is equal to 2, then there is no difference between theorem 3 and 4. That is, in this case, those operators are contractions on L2, and they are, of course, then bounded. But if we go beyond this range of the maximal kappa, which is kappa over d, kappa of d minus alpha over 2, then there is immediate explosion of the semigroup. So either the explosion is either the semigroup is a contraction or it explodes, this Feynman-Kac semigroup. So that's the presentation of the results that we got, and I would like to say a few words about the notions and objects that play a role here, but maybe there are questions, so that maybe I should wait for a moment.
May I ask?
Yes.
You talked about the optimality in sense of the best constant, but can you prove also the criticality, meaning that you cannot add in the right-hand side another positive term?
Maybe I don't know the criticality. Maybe one could extract somehow from this part something smaller. Probably not by conditioning, but by some clever arguments trying to estimate. And so if I understand your question, maybe there is some potential here in this reminder, because we really have identities.
Yes, I believe so.
Thank you.
Is there?
Sorry, can you repeat for what values of parameters theorem 3 and 4 give the same estimate?
For P equal to 2.
For P equal to 2? No, but
yes.
But in the theorem 3, there is D minus alpha, minus 2, yes?
D minus alpha over
minus
P.
alpha. Alpha is, what is alpha?
Alpha is the differential order of the operator.
But okay, so in theorem 3, there's D minus alpha divided by P. In 4, there's D divided by P star. But if P is equal to 2, then P star and P is the same. So it is different constant. If I look at it. Or maybe P, if P is equal to 2, then P star is the same, yes?
Yes, yes.
But constant are different, D minus alpha and D divided by P.
I understand your point. It should be the same D minus alpha over P star, I believe, but let me check that. Maybe I just copied.
Okay.
Yeah. It is less restrictive, and maybe I will have my recollection in a moment.
Okay.
Yeah, that's a good point.
Krzysztof, and
yes.
you think there is kind of a curved version of the results, not on RD, but on some other symmetric spaces? Or?
So the methods really use only Markovianity of the semigroup. So probably yes, if you are familiar with such contexts, you could try to do it. I mean, a lot of this is general. There are some special calculations which I plan to show in a moment, and those calculations depend on some specific knowledge about the operator in the semigroup, and that requires expertise, which I probably don't have in this case that you asked.
Okay.
And let me see. Let me check immediately the constant. Sorry, I probably have hidden this from you. I have this constant, so probably this is correct. I will try to make somehow react to it more better later on. So let me go to insights.
Can I just ask one small question?
Yeah, yes, please.
Hi, this is Jerry Goldstein. I'm enjoying your lecture very much. Can you write down the kappa in the special case when in 3 dimensions when p is 2 and when you're dealing with the Cauchy process rather than Brownian motion? So the exponent is 1/2.
Yes, yes.
Can you write that? Can you write down explicitly what kappa is?
Let me see.
What its best constant is?
Yeah, there are some specific questions that I maybe this constant, right?
Yeah.
That's p equal to 2 in a sense.
Yeah.
So alpha equal to 1. That's a 2. D is equal to 2, right? So we have 3/4. Okay, that exceeds my knowledge about. That's 1/4. So gamma of 3/4 squared and gamma of 1/4 squared in the inverse. So yes, okay. In a sense, yes. I cannot really comment on the value of this value.
That's okay. That's pretty explicit. Thank you.
So the constants. So the insights. I really think it's about about Markovian semigroups, and this Bregman divergence somehow agrees well with those notions. And my specific Markovian semigroup is generated by this Levy measure in the sense of the Levy-Khinchin formula. This Levy measure is defining the characteristic Levy-Khinchin exponent. And this PT is can really be defined as by Fourier inversion from this Fourier transform. That's no surprising. In particular, we have alpha equal to 1 and the Cauchy process here, or the so-called Poisson kernel. And of course, this is a convolution semigroup of functions, and they are actually transition densities. And in this case that is discussed here, they are translation invariant, space invariant. And here's the usual notion of the semigroup, which acts on appropriate spaces. There are plenty of spaces which make it reasonable to consider. For instance, there are plenty of references. One of them is a paper by Kwaśnicki. So that's the semigroup. The kernel of the semigroup, here I'm just using one argument because it really depends on the difference of 2, has this scaling property, which is well known and easy to check by Fourier inversion, and has this approximation, which has the on-diagonal estimate and the off-diagonal estimate. And the nice thing about this PTXY is that is estimated from above by the Levy measure. That is, PT over T is estimated by the Levy measure times a constant, which is very convenient in our development in this paper. If such a bound is not satisfied, then one needs to be a bit more careful and use probably more sophisticated tools to consider the existence of the P forms. And also, which is less special, we have a weak convergence to the Levy measure as T goes to 0. Okay, now we take 2 functions. one in LP and the other one in conjugate LP, so to say. And we consider this form, which is the usual form which is considered for the Dirichlet the quadratic forms. And we consider this, everything is well defined, convergent, and so on. And here's a simple result. This P form for our fractional Laplacian, but certainly in much more general situation as well, is a limit of this, such expressions when we take this approximate quadratic form, or bilinear form maybe, and apply it to function u and u to the power p minus 1. So this is good for every u in LP. This limit exists. It may be infinite, but it always exists. And if u is in the domain of the generator, then this P form is expressed as the pairing of the generator on u and u to the power p minus 1. So that's basically all the mystery about the P form. Okay, so let me go on. And this special knowledge that we have about the semigroup of the fractional Laplacian involves the representation in terms of the Gaussian semigroup. Because at some point we need to calculate explicit constants, so we need to have a device to calculate, and the device here is the Gaussian kernel. So here's the so-called subordination. Here's the semigroup on the half line, the so-called subordinator, convolution semigroup, and it somehow changes the time in the Gaussian kernel GS. S is time of the Gaussian Gauss-Weierstrass function. So here's some notation. So I'm sorry for that. F is a power function with some specific exponent. It's a power function on the line. T plus means that it's 0 to the left of 0. And constant is so chosen that as we integrate f against pt with respect to time, then we get x to the power negative beta. And that's some simple algebra that makes this happen. And the constant.
Sorry, what are g and eta in the first formula?
Yeah, G is the Gaussian kernel. It's the semigroup of the Laplacian, and eta is the subordinator. Subordinator has Laplace transform e to the power negative t times, okay, maybe u to the power alpha half. The subordinator should have the Laplace exponent u to the power alpha half. I did not say it here. Yes, okay. Thank you for the question.
Thank you.
So there are some specific calculations which are possible thanks to Gaussian kernel indeed. So one specific thing that comes from the definition of H is that PTH is less than H. This is kind of trivial, but I'm not explaining that here, because somehow we shift the integration defining H. And H is this kind of potential. So in this sense, H is superharmonic or excessive. Then we also consider a singular object for the derivative of f. Remember, this is a function on the line. And we divide it by H to somehow mimic what we had in this ramification of Fitzsimmons. So it's somehow this weight of Fitzsimmons. And then this function Q is x to the power negative alpha by some simple algebra times a constant, and this constant is our kappa. So I'm just giving you some information how it works, what's the mechanics of it. And the important fact here is that the Feynman-Kac semigroup corresponding to this Q also makes this H superharmonic, which is quite a strengthening of this property. So we kind of use the room that we have by this Fitzsimmons ratio. Okay, so let me say how we get those identities, Hardy type identities, and I cannot tell too much. It's on one hand elementary, on the other hand is quite complicated. So we get the Hardy identities for the P form by considering this expression. So this approximate bilinear form applied to H times V, and this application to a product of functions is really the essence of Dup's conditioning. So we are using Dup's conditioning here and some kind of rearranging of terms. So that's about theorem 1. Here's an insight on theorem 2. In a sense, this function U, being the minimum of 2 power functions, reverses Hardy inequality in the sense that for this function, the Hardy inequality becomes equality, or actually reverses sign, if kappa beta, for this beta, is greater than kappa of d minus alpha over p. So in simple terms, we take this function as a test function to show that one cannot improve the constant in our optimal Hardy inequality. The pleasant thing is that this function does not have required LP integrability, so we need to approximate those the function by some test functions. And that's a little bit annoying because we need to approximate and respect somehow the EP forms, which we don't know enough about the linear space structure of the domain of the P form. The domain of the P form, I don't think I told that, is the class of all functions for which the P form is finite. So that's about the theorem 2. And here's then some insight on theorem 3. I want to perform some formal calculation here. Let F be the domain of the fractional Laplacian on LP. Let U be the solution of the Cauchy process corresponding to the Schrödinger operator. So we apply the Feynman-Kac semigroup to F. Then formally, that is informally, that is formally, we differentiate this expression in time. So the P integral, the integral of the P power of U. So excuse me, those formal manipulations. We want to differentiate this expression. We use the chain rule. We use how we differentiate the absolute value to the power P. We get the French power. And here we will get the generator. Here's the generator, because U is given as by the semigroup of this Schrödinger. The Schrödinger operator, Q is this potential. And now the product of the first two terms gives us the negative of the P form. And the second term is just the Q times U to the power P, the absolute value U to the power P. And if we know that this is negative, which we know by the Hardy inequality, that we know that this is not increasing. So the norm is preserved. And this is good provided we have Hardy inequality, in particular provided that kappa is in this interval from 0 to the maximal, the optimal value for this given exponent P, because somehow P was fixed in this calculation, of course. So that's the insight on theorem 3. And here's the insight on theorem 4, which was about the range of boundedness. You see, I have d minus alpha over p star. Okay. So I really need to check afterwards about my exponent. Okay, so here we actually have it easy because already we know the approximation of the heat kernel of this Feynman-Kac semigroup. It's given by this expression where the third factor is the approximation of PTXY, the semigroup of the fractional Laplacian. And here are the two extra terms which really are the mass of the semigroup, the eventual mass of the semigroup when it starts at X. I would interpret it this way. So that's super probabilistic, but finite, provided that kappa is less than the best constant in the Hardy inequality, less than or equal. And now with this singularities at 0, we can prove or disprove boundedness on LP quite easily. And this follows if beta is less than d minus alpha over p star. Okay, the approximation of the semigroup is given in our previous paper. So it was kind of a free lunch here. So I have maybe my time is slowly finishing. So just a few insights. That will be just general remarks. Recall, in principle, this is our P form, at least for nice enough functions. We have this approximation, but using this approximation may result in a loss of focus or accuracy, and we would not be able to get our information about the semigroup, of course, if we are using this approximation. Actually, even this symmetrization may be problematic because if we replace the Bregman divergence by a symmetrized version of it, sometimes we are not always sure what to subtract and how to do some arguments. So our experience suggests that one should use FP as long as possible and then only present the results with the symmetrized version. Okay, here I have some connections about the existing literature, and that's a very large body of papers. Here are some there are some basic calculations with forms and powers. Varopoulos, that's 70s, if I'm not mistaken, already used this EP to capture evolution in LP of functions about the action of operator semigroups. The comparison of EP of U and E of U P over 2 can be traced back to papers of Siemionov and Liskiewicz. And there are papers of Struk, the famous paper of Karlen, Kosulka, and Struk, for instance, and these papers were cited already, but I don't remember the authors here. And this is about one-sided comparisons. Sometimes people initially were a bit afraid about the signs. As for local operators, I have some references here. This LP setting was important to study perturbations of Markovian semigroups. There's a large body of work by Farkas, Jakob, and Schilling, especially the monograph of Jacobs, and also by Hoch. And they have their approach to especially the bivariate forms is of interest. And there are some recent developments by Damir and Professor Siemionov. And there are some probability and martingale connections which were really inspiring us. I mentioned them here, but my time is finishing, so maybe I will stop here. And if there are questions, I will be happy to answer.
Well, thank you very much, Krzysztof, for the talk. So, are there any questions?
I have a question, if I may. Krzysztof,
yes.
I want to ask you: have you looked at gradient perturbations?
We did not consider in this setting yet gradient perturbations. Let me tell you what is pleasant about Schrödinger perturbations. You can approximate them from below by bounded perturbations. I don't know how to do it for gradient perturbations, so that requires a separate approach. And of course, with the gradient perturbations, we immediately use the symmetry, so that's another problem. Symmetry seems to be important here at places. I'm not sure for larger generality, but we were using freely what we had at our disposal, and the symmetry was part of it.
Krzysztof, could you send the talk slides?
Sure.
Thank
I
you.
will do it right away.
Can I ask another question if nobody else has a question? Krzysztof, so one can say that basically you find yourself in the situation where you have basically where you can work in LP, but not in L2. So you do not, basically you work directly in LP rather than going through the L2 theorem. And so I have a rather vague question, but what is, can you comment on sort of the general picture stuff? You mentioned the program, your research program, and in general, this phenomenon when you work in LP rather than, where there is no L2 theory, but there is LP theory, sort of that way. Do you have any comments?
Yes, so here the comparison of the best constants show that it may be beneficial to work on LP without the help of L2. So that's indeed the one point. We get identities which we would not get if we use inequalities, because by definition inequality is not identity, of course, and somehow the identities are convincing. So for instance, we have something which we call Douglas identity for p-forms. Let me comment of the scope of it. So somehow it looks like this Bregman divergence is a way to capture the evolution in LP of Markovian semigroups. At this point, I think that's the applicability of it. It's modest, but I think useful. So maybe this will be useful for constructing or estimating the semigroups, as we have seen here in one special case. Okay, so that's one setting, the semigroups. The other setting are martingales. This is very similar in a sense to semigroups, in the sense that semigroups give martingales under some assumptions, or maybe martingales show similar patterns of evolution as semigroups in a sense. So anyways, one can sensibly use this Bregman divergence to study martingales in LP. And the third setting is to study harmonic functions. Of course, the second and the third setting of these harmonic functions, they have more probabilistic flavor, because somehow we are using stopping times, harmonic measures, and so on. But again, this Bregman divergence is loss-free way of measuring the increments in LP somehow, as the gradual increments in LP. So now in the setting of harmonic functions, we have those Douglas identities. And for semigroups, we have also the so-called Hardestein identities, which we also have for harmonic functions. So this thing is growing. I don't know where it will take us, but it seems like a reasonable program to follow at this moment. I could show you a Douglas type identity or Hardy type identity, Hardestein type identity, but maybe that's already too much. So the setting of semigroups is a simple one and a pleasant one, so maybe this shows the usefulness most.
Thank you.
Well, if there are no other questions, let's thank Krzysztof.
Sorry, I would like to make a comment on this constant in Theorem 4.
Thank you.
Problem with it. The fact is that when I looked into the proof, that both constants in the text are wrong. We have the constant in the paper, we have a constant which is given in this theorem, but it should be, it would be correct constants if this function kappa be increasing on a whole domain, but it increases and later it decreases. So the condition for boundedness is that delta, this exponent in the estimate of the function p tilde, the semigroup, it must be smaller than d over p star. Delta must be smaller, but it doesn't correspond to the to this kappa. If delta over p star is smaller than this maximum, the point when the kappa attains maximum, so d minus alpha over 2, then this constant is correct. But if d over p star is bigger, then this constant is just the Hardy constant, the kappa. So
thank you. So we are talking about
you have to correct it, I think.
Yeah, so I will correct and send it to Dmitry. So that was about the constant in Theorem 4, and I presented 2 of them. And somehow, sometimes it's useful to use this kappa function. Sometimes it's better to use the argument. That's the minor thing, but that's about this beta, or sometimes called the delta in our notation. So as you can see, it's a little bit easy to get lost in those notations. Thank you, Tomasz. I will send the corrected file with the slides later.
Thank you. Are there any other questions or comments?
Hi, Bogdan, very nice talk. You wanted to tell me a story, but unfortunately, there's another talk. I think maybe people are going to attend the colloquium now. So maybe if you don't mind emailing me the story that you were going to tell me about Stein and your picture. Is that okay?
I will tell you about what the story is, and maybe some other time I will tell the story.